Welcome to MEERTALK. My name is Kaeza, your host for today. We are very glad to be getting together for another MEERTALK. Today we will be hearing from Jim Massa, and then we'll take questions from somebody in the MEER community, and after that we'll open it up to all of you for some questions. In case you didn't see our recent newsletter, Dr. Tao was a presenter in the Cooling the Earth Technology seminar, which brought together a diverse group, all committed to mitigating climate change. You'll want to take a look at our redesigned newsletter with more information and fabulous photos. In order to carry out all the projects crucial for MEER's further development, we do rely on donations. If you haven't already donated and you would like to contribute toward our efforts to cool the planet, we really appreciate this. You can go to meer.org/donate. And thank you so much for everybody who is contributing. You could also write to info@meer.org if you want to be in touch. Now, let me tell you about our guest speaker. Jim Massa is a trained scientist with a background in oceanography and years of experience in Arctic climate change research. His work has provided valuable insights into the efforts of global warming on marine ecosystems and polar environments. In addition to his research, Jim has dedicated much of his career to education, teaching science and mathematics at levels ranging from middle school to undergraduate courses. If anybody has any questions that come up while Jim is presenting, you can go ahead and send them along to Barbara in the chat. Okay, Jim, well, thank you for being with us, and we are very eager to hear what you have to say about the warming waters and the Arctic.
Basically, I'll be talking about how ocean dynamics are really the main driver in climate, and with, of course, what takes place in the Arctic. So I think it's important to at least to lay some background information. And oceans are very important in controlling climate. They have absorbed over 93% of heat energy that has been generated from the burning of fossil fuels. So much heat has been absorbed by the oceans that we actually now measure it in terms called ocean heat content, OHC. And over the past 70 years or so, it is now estimated to be an accumulated more than 520 zettajoules of energy. And of course, zeta is the prefix is 10 to the 21. And of this amount, approximately 68% is trapped in the upper 500 to 700 meters. The atmosphere is just 2%. All the ice, sea ice, alpine ice, land ice, about another 2%. The rest by land and entropic loss to space. That's where the energy has been absorbed, where it's gone. So because of this huge amount of energy, the oceans really drive the climate in my assessment. So here's a breakdown of where the global warming is going. As you can see, 93.4% to the oceans, 2.3 to the atmosphere, 2.1 to the continents. Between glaciers and Arctic sea ice, it's about 1.7%, and then another 0.2% for Greenland, another 0.2% for Antarctica. If you were to add up all these numbers here, it's 99.9%, and the remaining 0.1% is entropic loss, the space and so forth. But oceans is where all the energy is going. And for the longest time, the ocean's really been saving our bacon by absorbing all this heat energy and CO2 that until recently, it was being sequestered to depth. That is being reduced. And now that's another reason why we see the accumulation in the upper 500, 700 meters is because, as I'll explain later on, the oceans are stratifying and the heat it limits vertical movement. So now the heat starts accumulating in the upper several hundred meters. So how do oceans absorb heat? Well, it could be via direct sunlight absorption. Big if the sea conditions are calm. Usually they're not. You know, there's always turbulence, wave action that impacts, reduces how much energy can be absorbed uh, into the ocean directly from sunlight. Mesoscale eddies is the main mechanism for how heat and gases move into the oceans. So, what's a mesoscale eddy? Typically, these are mini gyres that are on a scale of about 100 kilometers or less in diameter. They can rotate either clockwise, which is in the northern hemisphere is referred to as anticyclonic, or they could rotate counterclockwise, which again in the northern hemisphere is referred to as cyclonic. And it flips, it's opposite in the southern hemisphere. And that's due mainly to the Coriolis effect. So now the question is, what are gyres? Well, they're rotating systems and found in the atmosphere and in the ocean. Oceans are large scale, in the order of several hundred kilometers to several thousand kilometers in diameter. And they result from balancing what we call pressure gradients, the Coriolis effect, vorticity constraints. So all these factors get balanced out, and you have a gyre that results because Earth is a ball that rotates, and there's a lot of liquid on it that sloshes around, and because of the rotation of the Earth, you're going to have buildup of water on one side of the ocean basin. That sets up a pressure gradient, and then you have to balance the Coriolis, the vorticity, which is a fancy term for tendency to rotate, and you get gyres. So now in this slide here, this is the Gulf Stream. Most people think of the Gulf Stream as a big ribbon that shoots up the east coast of the U.S. and moves over the Atlantic. It's actually a series of mesoscale eddies. All these little circular things that you see, those are mesoscale eddies that pinch off the main flow. And these mesoscale eddies can rotate clockwise or counterclockwise. And how they rotate determines which way materials move, whether it moves into the ocean or from the oceans back to the atmosphere. So these are all examples of mesoscale eddies, which is, again, based on physics and so forth. And to show you like the large gyres overall, you got the main one here in the North Atlantic. You have in the South Atlantic, the Indian Ocean, the South Pacific, North Pacific, and some of the identifying major currents. But you also have smaller gyres, for example, off in the what's called the Norwegian, Greenland, Icelandic Sea. There's a counter clockwise rotating gyre, as well as the Gulf of Alaska is another counterclockwise rotating gyre. But most of the major gyres in the world's ocean they rotate in a way that you have a convergence zone in the middle, which resulting downwelling. So the middle of the oceans are basically biological deserts. Because of the downwelling, you don't have nutrients being injected into the photic zone. And keep that in mind later on when we talk about deep water formation and so forth. So this just gives you an idea of the major oceanic gyres on the planet. And again, this one shows that gyre in the Greenland, Icelandic, Norwegian Sea, Gulf of Alaska, and shows a little bit better some of the major currents here. Remember, all these gyres are going to result from balancing pressure gradients, vorticity, and Coriolis. The mathematics is quite interesting on it. So back to mesoscale eddies. They're often referred to as the weather system for the oceans. Due to their rotating nature, they can either move material from the atmosphere into the oceans or move material from the oceans to the atmosphere. The main thing we need to keep in mind is that the oceans and the atmosphere are a coupled system. They're not separate. They're a coupled system. So in the northern hemisphere, if a gyro, mesoscale eddy, as I'll start referring to as ME, if it rotates clockwise, which is anticyclonic, it has a convergence zone in the middle with the resultant downwelling. These convergent mesoscale eddies allow heat energy and gases to mix into the oceans. If it rotates the opposite direction, cyclonic, then it has a divergent zone in the middle with the resultant upwelling, and these divergent mesoscale eddies can then move heat and gases to the atmosphere. So that's important to keep in mind as you construct budgets as to what is the net heat gain or loss into the atmosphere, into the oceans, and so forth. So to repeat, if the mesoscale eddy has a downwelling in the middle, temperature, heat energy, gases, and so on are going to move into the ocean. If it's an upwelling, then they're going to have material, whether it be outgassing back to the atmosphere or heat diffusion back to the atmosphere, but that will happen. So now how do oceans distribute heat? Well, horizontal currents. That's pretty much typically induced by wind stress. So for example, all the major currents that we see on the surface, the gyres and so forth, that's all heat energy from the sun that induces temperature differences, that induces pressure differences, that creates wind. The wind blows across the surface. You get and it's called wind stress. The water moves as a result. So that's one way. So you can take heat, from say lower latitudes, move it to higher latitudes, which, for example, the Gulf Stream does. Then you have the vertical currents. We refer to them as thermal Haley currents. These arise via differences in density, which is a result of differing temperatures and salt content, which is called salinity. If you have denser water sitting over less dense water, it will sink vertically down. So those are like major movements. A slower method is what's called double diffusion. It's a complex process by which heat and salinity are mixed and distributed. Heat usually mixes at a faster rate than does the salinity differences. You could have simple diffusion to the atmosphere, which, by the way, we are seeing more and more of because of the stratification that is increasingly taking place in the oceans. And when you have brine rejection during the formation of sea ice, that creates thermal Haley currents because when you form the sea ice, you are kicking out the salt content. Well, now you have a higher salt content in the surface layers. It's denser, so it's going to sink vertically down. You probably have all seen videos from the Antarctic region where you actually see the plumes of the dense water sinking as the sea ice is forming. Sea ice is basically, you could like take a chunk of it, melt it down and drink it because the salinity is very, very low because that salt pretty much gets rejected out. So these are the major mechanisms by which the oceans distribute heat. And this is just kind of a double diffusion in the ocean. It's just it's a quick little summary. Solar heating heats the top, the top producing waters, which are, if it's warm, it's going to be lighter because of expansion. So it means it's less dense. And it could also be salty water, which higher salinity content also makes it more dense and can sink. Now, one of the questions that always question
No, go ahead.
One of the one of the questions that always comes up is which is more dense water, warm salty water or cold less salty water? And the answer is it depends, because the higher the temperature, the less dense it is, but the higher the salinity content, the more dense it is. So what happens is you have to then look at what's called the buoyancy factors, and water will sink to where it meets its buoyancy factor. So it will sink to a layer of similar density. And then you can still get some mixing and so on. So the heat does diffuse faster than the salt. That leads to instability. So if you lose heat, that will increase the density and can carry salty water downward. This is what happens in the North Atlantic. You have the warm, salty Gulf Stream water coming from, the Gulf of Mexico, equatorial Atlantic. It moves to, off the UK, the Nordic countries. It gives off its heat, diffuses the heat to the atmosphere. Well, it still has the same salt content, but now it's colder because it's given off its heat. So now it becomes more dense and it sinks. That is the start of the vertical sinking, what we call AMOC, the Atlantic Meridional Overturn Circulation. It's as simple as that. Give off its heat, it's still very salty, but now it's cold and very salty, it sinks. That is basically what thermohaline flow is. But because of the way heat and salt diffuse mix differently, you get what's called fingering, salt fingers. And you see these little projections of, these plumes of heat, these plumes of salt. And what eventually happens is, again, going back to what I talked about the buoyancy forces, you can get a layering or stratification that then gets separated by zones of turbulent mixing. So, for example, in the oceans, typically during springtime, you will have an overturn of the water column induced by wind, mixing, the heavier water at the top sinking and then the lighter water rising. So you get this vertical turning, but then you get either thermocline or a pycnocline. Thermocline is a sharp change in temperature. Pycnocline is sharp change in density. We also get haloclines in the Arctic Ocean. That's a sharp change in salt. So you then get what we then call a mixed layer in the ocean. And this is where you get productivity, because you lock in the nutrients within the photic zone. Phytoplankton can do their thing, so on. As we're going to see later on, you do need to have these thermoclines, pycnoclines break down to allow re-injection of nutrients. And what we're seeing in the oceans these days is the stratification is increasing and becoming stronger, so that this is becoming more difficult to inject nutrients into the photic zone, which is reducing net primary productivity by the phytoplankton. This is extremely concerning. So what impact does ocean heat content have? Well, thermohaline flow takes the heat and the CO2 to depth where it's sequestered. And this is what oceans have been doing for a very, very long time. That's why I say the oceans have been saving our bacon until recently. But as the oceans continue to warm, the thermohaline flow slows down. Sequestration to depth slows down. This leads to increased heat building up in the upper water layers, and in turn leads to increased stratification in the ocean layers, where the heat, and now the CO2 for that matter, are now trapped in the upper layers. This trapped heat leads to increased sea surface temperatures, SSTs, and also diffuses to the atmosphere, increasing atmospheric temperatures. So as a reminder, 68% of that absorbed heat is trapped in the upper 500 to 700 meters. And as I just alluded to a few moments ago, increased stratification and major implications for net primary productivity. it's rapidly decreasing due to nutrients not being mixed into the photic zone. The photic zone is defined as the depth at which sunlight energy can penetrate down to. Sufficient enough to activate the electron transport chain system inside the chloroplast of the phytoplanktons. So where the stratification occurs, it does act as a barrier preventing vertical mixing in the water column. So, and we're seeing this. Here is a graphic showing the stratification in the oceans. These are showing thermal bars, and you can see they're very closely packed together. And down here, the scale you see goes from 0 to -60, 0 to +55. That's latitude. And not surprisingly, we pretty much have almost a permanent thermocline in the tropical waters. So everyone says, oh, let's go, snorkeling or scuba diving in the tropics because the water is crystal clear and you can see a long ways. Yeah, because it's also biologically poor productivity. And it's because of this near permanent thermocline that you can't get nutrients into the photic zone and have the phytoplankton do their thing. If you see in the areas you start going to like 30 degrees south north latitude, you can see the thermal bars start bending to the surface. That is allowing materials to be mixed into the water column in the photic zone. But you can see, for example, down about 1,000 to 1,500 meters and down to 2,000 meters, very tight thermal bars. This is where we get into an area where it's called a permanent technocline in the oceans, down to about 2,000 meters. And when you start getting to the deep portions of the oceans, it's pretty much uniform situations. So this is getting worse. The stratification is intensifying.
Could you just repeat that last part about when you're getting just on that last slide? There was a little lag in your audio, and I just want to make sure we understand. So you were saying
when you get to the abyssal area, if you look at the wide spacing of these bars here, this is showing pretty much uniform oceanic conditions. Think of when you look at a contour maps, and when you say looking at a topo map, and the contour lines are really close together, that indicates a very steep gradient. And if they're far apart, it's a shallow gradient. Sort of the same thing. We're actually following gradients in the ocean. Mm-hmm. And this is showing the global stratification change in the upper 2,000 meters. As we can see, and this is in 10 to the minus second per second. So it's an acceleration. And we can clearly see that the stratification rates are accelerating. That's what this is telling us, which will reduce ocean productivity. And considering how many billions of people get their protein from the oceans, this is not good. Throw in ocean overfishing, and yeah, oceans are hurting, to be quite blunt. But this shows that just like with sea level rise is definitely following a nonlinear increase, meaning that the second derivative is not zero. So same thing here, just stratification in the oceans, the second derivative, the acceleration is not zero. This is alarming, in my view. This is showing the ocean heat content. This is the scale is given 10 to the 22 joules, but it's just going up and up and up. And you'll notice about in 1990, the mid 90s, and so on. I'll show later on. In my assessment, the planet overall went past the tipping point in the mid 90s. We start seeing the accumulation of this heat energy in the upper layers of the oceans. And this heat is not is going to move around, and since it can't move vertically downward to be sequestered, it's going to move horizontally. It's going to move vertically upwards, and we see this increasing. The red graph shows a 3-month average. The black shows the yearly average, and then the blue is the pentadal or 5-year running average. But it's unmistakable. And even if you just want to say this is a straight line, it's not. The function is nonlinear. But just for simplicity's sake, you just integrate under this curve here, and that's how you get the approximate 520 zettajoules of accumulated heat energy in the oceans. So, and it continues to increase. It just does because we're continuing to burn fossil fuels. This is the work of Li Chang. He creates a yearly update to the ocean heat content, increasing around the major oceans. So each of these little boxes is a region of the ocean. For example, the Northwest Pacific. Then he has the Indian Ocean down here. I guess that's what turquoise box. The blue box is the tropical Atlantic, and so on, and the Mediterranean. And the North Pacific, North Atlantic, Southern Ocean, with the exception of the Northwest Pacific, and it's kind of interesting, the heat content in all the major oceans are increasing. And it looks like the Northwest Pacific increased and then kind of flatline. Almost looks like a cube root function in some ways. But all the Southern Ocean is really increasing. All the ocean. This is ocean heat content increasing just about everywhere. The one place I draw your attention to is the Mediterranean. And I'll explain why this is important. This is racing away, the heat content in the Mediterranean. And hopefully it will become clear why that's important in a few minutes. But this is showing how the heat energy is accumulating in the oceans worldwide. And this is the change in global ocean heat content for the upper 2,000 meters. And this is this big red arrow that I placed on this graphic. And this is showing, and this is my assessment here. In my assessment, the planet overall went past the tipping point during the mid-1990s. And the reason is the accumulation of ocean heat and the heat no longer sequestering to depth. And it just continues to increase and increase. And it's getting more so. And this, when you also, take into account lag effects and then what's called pipeline warming, we are experiencing the CO2, I like to use the term CO2 equivalent, because that includes not just CO2, but methane and nitrous oxide. When we look at the CO2 equivalent levels of 10, 15, 20 years ago, what those levels were back then is what we are experiencing now. So if we want to know what current levels effects will be, wait 10, 15, 20 years, and we're experiencing it then. And there's also pipeline warming. We can go to net zero right this very instant. You still have thermal inertia in the system that's going to keep warming things up. So prognosis is not really good. I mean, if you look at the work of, say, PIK group, the Potsdam Institute of Climate group there, they're already assessing we're past 1.6 and we'll hit 2.C some point before this decade ends. And they do their own assessments, and what they're projecting should be concerning to all of us. So I actually consider this one of the most important graphics in all of climate science, this right here, ocean, because you can clearly see it in the mid-90s, there's a switch from heat energy being sequestered to depth, and now it's being kept in the upper layers. And these are really cool graphics showing the distribution of the heat energy. This is the North Pacific. You can see here's the west coast of North America. This is Gulf of Alaska. Here's the Aleutian chain. So this is Alaska. Over here is Eurasia, and it goes from about 30 north latitude up, the North Pacific down to 400 meters. And this is showing the anomaly, which is reflectance of the heat energy being trapped. This is like the middle of the gyre, so it gets very concentrated there. But this heat energy here is not going to just sit there. It's going to do something. And what that something is going to do is, well, some of it's going to go through the Bering Strait into the Arctic Ocean. Some of it's going to diffuse. Some of it moves southward and ends up in waters that upwell around Antarctica, along with waters from the Indian Ocean. And when you have that heat energy and it upwells around Antarctica, it does what? It melts the sea ice there. It melts any cantilevered land ice that protrude out over the ocean. That's another reason why we're losing the sea ice at both poles, and Arctic and Antarctic regions. Here's a similar one for the Atlantic. Okay, so here's Africa, here's Spain, is Strait Gibraltar there. And see this plume here? That's waters from the Mediterranean. And this water from the Mediterranean, it is very warm, but it's also extremely salty. It has some of the highest salinity in the oceans. So because it's very salty, it sinks, but it sinks to mid-level depth to about 700 to 1,000 meters deep. And at that point, it's called the North Atlantic Intermediate Water. And well, that's right here, Mediterranean Intermediate Water. Keep that in mind when I show you a graphic that's a particular favorite of mine. So what does this have to do with Arctic warming? Okay, it's not just air temperatures. The Arctic is warming mainly through inflow of warm ocean currents. There's the extension of the Kuroshio current in through the Bering Strait, and you just saw the heat blob in the Pacific. This brings in warm water, and the flow rate is the volume is increasing as well. Then we have what I just mentioned, the NAIW, the North Atlantic Intermediate Water. That's the main source of warm water into the Arctic. The NAIW originates in the Mediterranean Sea, which is warming rapidly. This heat is brought into the Arctic Ocean, diffuses to the atmosphere, warms the water, melts the ice, and is a major contributor to what was called the Atlantification of the Arctic. By that, I mean we're bringing in warmer water, but it's also saltier water. So we're actually increasing the salinity of the Arctic Ocean, which historically has always been somewhat lower due to, riverine input, melting of ice, lots of precipitation, always tended to dilute the salinity. So ocean heat content is the main reason why the oceans are warming. Surface layers are warming much higher than the deeper layers. It's a major reason why sea ice is melting and the cantilevered land ice is melting. I continue to make the argument that it's the OHC that is causing a lot of our problems. So this is a cross section, and yes, it came from an exam, but okay, but it's still useful to illustrate the water masses, because the oceans are not one just big thing of water. We actually have ocean water masses that are defined by characteristic salinity and temperature parameters and profiles. So we have warm water. It sits on top here. Then you have this Antarctic intermediate water, which kind of flows, northwards. Here's the Mediterranean water that you see this arrow that goes towards Greenland. And you see this North Atlantic deep water. You see these arrows going down. Oh, this is AMOC. Here it is. This is AMOC right here. And it is, the warm waters of the Gulf Stream give off its heat, becomes very salty, very cold, and it sinks. It sinks down because it's cold and salty, so it's more dense than the warm, salty water of the Mediterranean intermediate water becomes the North Atlantic intermediate water. It then goes underneath it, and it flows flows southward all the way off Antarctica, where it upwells. This is the upwelling. It's upwelling because as it interacts with other water masses, the friction imparts some heat, so it expands, makes it less dense, and starts upwell. Well, that brings nutrients with it. And where it upwells is called the Antarctic Divergence Zone. And these nutrients helps make the Southern Ocean the most productive open ocean areas on the planet. It fuels all the baleen whales, the krill, and so on and so forth. There's also deep water formation off Antarctica. People are unawares of that, but you have deep water formation off Antarctica, and it sinks. It's very, very dense water, so it sinks right to the bottom. And it also then fills in the Atlantic basin, and it moves northward. You can see its impact up to about 40 degrees north latitude. So this is a nice cross section of the water masses, the major water masses of the Atlantic Ocean. So to the Arctic Ocean itself, okay, we have, here's the North Atlantic current. This is that North Atlantic intermediate water that originated from the Mediterranean. It flows in through the Fram Strait. It follows over on the Eurasian side. And eventually it does start losing its heat as it continues its flow. But the water's getting warmer. There's more of it flowing in. So we're having added heat into the system. It's melting the ice. It's diffusing to the atmosphere. And this, of course, all this increases sea surface temperature. Beaufort jar is very important. We'll discuss that later. But these are all various currents. Here is the extension of the Kuroshio current going in through the Bering Strait, also bringing in warmer water. It tends to move towards the North American side of things. Between the Kuroshio extension and the North Atlantic intermediate water, these are the major ways that we're bringing heat into the Arctic. And there's a myriad of currents and flows going through the Canadian archipelago. The white area is the typical extent of sea ice. But what this is happening is that this is a graphic I like. It shows you how much. It gives you an idea. It's down to about 700,000 meters, and it's just bringing in loads of heat, and it's just warming the Arctic basin. And these little, I don't know if you can see here, these little like orangey squiggly arrows, those are plumes of heat to the atmosphere. You have the transpolar drift. There's an interesting thing about that. Transpolar drift is actually controlled by what's called the Arctic dipole. The Arctic dipole are two major atmospheric systems. You have typically a high pressure system on the North American side and a low pressure system on the Eurasian side, and how it shifts around will determine, for example, what sea ice flow patterns do. It can either be constrained in the Arctic Ocean or it can get pushed out through Fram. And then we introduce ice into the North Atlantic where it can melt, dilutes the surface waters, slowing down AMOC. So some interesting things going on there. So what are the ramifications of the Arctic warming? First of all, what happens in the Arctic does not stay in the Arctic. Right? Warmer Arctic leads to warmer global temperatures. Ocean heat content is moving in, it's melting the sea ice. We're now seeing that the sea ice melts earlier in the year and freezes later in the year. This leads to increasing open water time for the year. It's increased from 5 months to 7.5 months. So now more than half the year, we have more open water. Ice extent is decreasing, which is measured in square kilometers. How far it extends is decreasing. The ice thickness itself is decreasing, which means that the multi-year ice is going away. So if the ice thickness is decreasing, the ice volume is decreasing, so we're losing the multi-year ice, which is very alarming. In fact, in the Narrow Strait region off Greenland is some of the last vestiges of 7-year sea ice. The heat diffusing to the atmosphere is changing precipitation patterns. Freezing rain here, at least in the Arctic, is becoming more and more common. It is projected that snow will no longer occur by 2100 in the Arctic. I mean, here in Alaska, we're getting more and more freezing rain events, which just makes for treacherous driving conditions. But this is what we're seeing. We used to be about, October, here comes the snows. Well, the Arctic Ocean's staying open longer. That heat is diffusing to the atmosphere. We're now, instead of getting snow, we're getting freezing rain. And it just makes for crazy stuff. It can affect regional and hemispheric weather patterns, including the Arctic dipole, the Arctic oscillation, and the North Atlantic oscillation. These all are teleconnections, and they drive weather patterns. For example, we're seeing changes in temperature patterns, precipitation patterns across Europe, across the UK. I'm sure you've probably already noticing those effects. So now it comes down to, will AMOC collapse or not? It's definitely slowing down. I don't think it's on the verge of collapsing as we keep hearing in the media. And there's several reasons for that. Basically, for AMOC to collapse suddenly, we need a major influx of fresh water at a big sudden go. What's happening in the North Atlantic now does not meet that criteria. We're having melting, sure, but the water has time to get entrained. It gets moved over to the western side of the Atlantic basin. What research has found is that when you have a high number of icebergs breaking off and flow southward, and then they melt in situ all at once, that can disrupt AMOC and it stops. Well, if Greenland ice calves off, it melts, it gets entrained, the probability of having huge amounts of iceberg all at once letting loose and all at once melting is reducing more and more. So I don't see that scenario taking place. About 13,000 years ago, Lake Agassiz in North America was this big, huge lake. And it all of a sudden, all this fresh water was just dumped into the North Atlantic and AMOC stopped. The one condition that I am concerned about, and let me go back to the Beaufort Gyre. The Beaufort Gyre is trapping fresh water. If that was to be suddenly released, then it's possible we could see a drastic change in AMOC. So now, okay, the work of Wally Broker, he's been called the grandfather of climate science. He developed a lot of techniques that are still used today. He used radionuclides, isotopic fractionation, and he demonstrated the slowing, stopping, resumption of AMOC, the conveyor belts we call it. And by the way, it's his use of radionuclide that identified the different water masses we have in the oceans. So now, if you were to ask me 20, 25 years ago, what would be the implications of a stoppage of AMOC, I would have said, sure, it would lead to hemispheric cooling, probably growth of some ice sheets. Today, I don't consider it hemispheric cooling. I consider the cooling will be regional. So my apologies to the folks in the Nordic country in the UK. You're going to probably experience some cooler conditions for some time now. But I don't see it being hemispheric. I see it being more regional because of the global ocean heat content. My concern with AMOC slowing, I alluded to earlier with the North Atlantic deep water upwelling off Antarctica. If AMOC slows or stops, that upwelling can slow or stop, then nutrients will slow or stop going into the photic zone. That could cause problems for that ecosystem, the food web down off Antarctica. And that's what this graphic shows. It's the deep water upwelling off Antarctica, bringing in much needed nutrients to fuel that ecosystem here. Won't spend too much time on that. That's just to kind of give you an idea of that. And this is just showing the colloquial conveyor belt, move sinking, flowing, and then upwelling. What is important to remember is that all the oceans on the planet is really one connected ocean. Because when you look at the water masses, all these water masses come into around Antarctica and they leave around Antarctica. So you can think of Antarctica as the big train station hub or something. Water masses move in and move out, but all the oceans are connected. It's not like, the Indian Ocean's its own thing, North Atlantic its own thing. No, they're all connected. And as they're all connected, they're all moving materials and energy and so forth around the big coupled system in conjunction, of course, with the atmosphere. Okay, now probably what you've been wondering about. Why is my assessment that aerosol reduction has little effect on specifying sea surface temperature? Okay. First of all, water has a higher heat capacity than air, about 4 times more. Ocean surface can be turbulent, reducing energy uptake. The angle of incident decreases with an increase in latitude, so not all the incoming energy penetrates the ocean. What energy does penetrate quickly attenuates, so it follows an exponential decay pattern. Typically, putting aside the tropics, which is kind of the exception, typically it's just the upper 1 or 2 meters of water that are warmed directly from sun energy penetration. That's where the mesoscale eddy comes in, if they can mix it in and bring it to further depths into the ocean. But as far as this direct sunlight energy, typically just a couple, 1 to 2 meters, maybe sometimes 5 to 10, depending on locations and conditions. Atmospheric scientists themselves assess that reduction of aerosols will result in an atmospheric temperatures increase of 0.42 C over 100 years. That's atmospheric scientists' assessment. Factor in the higher specific heat of water and the rapid attenuation, the reduction of aerosol, the effects of aerosol reduction on increasing sea surface temperature is really not going to have any significant impact. Certainly not what has been claimed by, it's 5 to 7 C. Nope, that's just completely off base. Temperatures keep increasing because we keep burning fossil fuels. That's just what it is. Yeah, the ocean does absorb heat energy, right? But again, back to the mesoscale eddies. So aerosols are a factor for increasing air temperatures, but not significant for increasing sea surface temperatures. With the reduction in thermohaline flow to depth and increasing stratification, ocean heat content is diffusing upwards, increasing sea surface temperature, and adding to atmospheric temperature increases. So you can think of the ocean heat content like a battery slash capacitor. Before it was storing energy, now that energy is being discharged, and there's a lot of energy to be discharged. So this is a couple basic figures here showing how the sun energy, as you move up in latitude, spreads out. It's not as concentrated as saying, directly striking at the equator. So if it spreads out, there's less energy absorption. And this is, just showing a bunch of angles for latitude, longitude, all that kind of stuff here. But this declination angle, del here, sunlight energy comes in, not all of it is being absorbed. Basically, you take, if this is your angle here, you take the cosine of that angle. That's how much of the incoming energy measured in watts that gets absorbed in the ocean, assuming it's a smooth surface. If it's turbulent, you're not going to get much energy absorbed. So now, my other reason, my main reason here, why I don't think aerosols is as important a factor when it comes to not only the oceans, but also the atmosphere. The role of marine phytoplankton, marine algae, and bacteria must be factored in. These organs produce and release, okay, this is a mouthful, dimethylsulfonylpropionate, or DMSP, as well as dimethyl sulfide. DMSP reduces the DMS. So these compounds are released into the atmosphere on the order of 10 to the 15 grams per year. These compounds are aerosols. Recent research shows that these compounds that marine produces by releasing DMSP and DMS can regulate the planet's temperature and the climate. The planet gets too warm, more is released, too cold, less is released. In other words, marine producers introduce a negative or corrective feedback loop in controlling Earth's temperature. 10 to the 15 grams per year is a significant amount. And that does not include the aerosols from volcanic activity. Okay? So the problem, this is now where the problem with the ocean stratification shows up. If the ocean stratify and primary productivity decreases, that means there's less phytoplankton, there's less release of DMS and DMSP to help regulate the planet's temperature. Also, sea salt spray are aerosols, and they're released in large quantities, typically via wave action. And atmospheric scientists, they typically do not factor in DMSP, DMS in their analyses and models. And that concludes. Thank you.
Wow, thank you so much, Jim. That is a lot of complex information and very informative. We have a couple of people from the MEER community who would like to ask you a question or two. So first, we're going to bring on Peter Dines from the MEER team. Peter Dines is an environmental consultant and currently the managing director at MEER. Go ahead, Peter.
Thanks, Kaisa, and yeah, thanks, Jim. You never fail to enlighten us and to make us sit up and pay attention to absolutely critical information, which I wish more policymakers and people who pull the levers of power were very aware of and not in complete denial as some are. You've answered some of my questions in terms of the impact of shipping aerosols, which a lot of people are talking about recently. But maybe you could touch on that as one point in terms of what you think those reduction in shipping aerosols, what effect that is having. Also, I'm just wondering, the DMSP aerosols, is there a way to not, enhance those so that we can produce more of those natural aerosols to have a cooling effect? That would be a question. And lastly, in terms of, because you mentioned a lot about the thermohaline system. It's such a complex system looking at your talk. And obviously marine cloud brightening, and people are looking at trying to mitigate that thermal side of things, but you obviously have the complexity of the haline side. So is there a danger in terms of placing lots of, say, marine cloud brightening in certain areas or regions where you start to have an effect on the haline system as part of that thermohaline system, and you might actually end up with negative effects as well as positive, which might negate what you're actually doing. So my first question is, the shipping aerosols, is that having a big impact? The DMSP, can we produce more of that? And lastly was on the marine cloud brightening and effects of that.
Well, I'll do my best. As far as far as the shipping, okay, what we're seeing is that there is less clouds forming because we reduce the aerosol. In order to form clouds, we need what's called hygroscopic particles, for which the water vapor to coalesce around. And then once you start coalescing, you then build clouds and so on. So if you have reduced aerosol particles, there are reduced hygroscopic particles for the water vapors to coalesce around. So we have less clouds, and that allows more sun energy in. And that contributes to the Earth energy imbalance that we're seeing, UV in, IR out kind of stuff. But again, what's not included in the EEI, the Earth energy imbalance calculation, is the diffusion of the heat from the oceans, which, have a hell of a lot more of that energy in there. I mean, last time I checked, 93 is a wee bit bigger number than 2, but so there's just, you are actually setting up the conditions without having the clouds there. You are setting the condition for increased evaporation, increased heat from the oceans to the atmosphere because of the reduced aerosol. So again, it's the oceans playing the role. Now, as to introducing the end, that comes into the engineering scheme, and I'm not really that's really not my area, so I really can't really comment to that. That's more for the engineering folks. How would you make this compound? I mean, it's a chemical yeah, again, that's I'm a fluid dynamicist. I'm not a chemist or an engineer per se, so that's really not my purview. As far as the hailing, well, oh boy, that's a whole can of worms there, and we're seeing that in the Arctic Ocean. The Arctic Ocean is, it's a small body of water, and when we had the last ice age, the Arctic Ocean was really a lake because it was all surrounded by land, because all sea levels dropped. It was just surrounded by land. We are seeing major changes with the halocline and the movement of salt in the Arctic Ocean. The halocline is moving up and down. It's seasonal. It's just drastically changing, and it does impact how the water moves. As I mentioned earlier, the heat will diffuse faster than does the salt. Doesn't say the salt doesn't diffuse, it does, but we are seeing a major change in the halocline. Now, one of the things, because of the influx of this water from the Atlantic, the Atlantification is bringing more a higher salinity content into the Arctic Ocean, and that is affecting the halocline, which affects the density profile of the water column. So now we're starting to get, if it's showing, it could actually lead to more mixing, which allows that warmer water that was deeper in the water column to now come up to the surface of the Arctic Ocean. Because typically you had warm, salty water, but the overall density was more than the cold, less salt water of the Arctic Ocean, that it was below it. But now we're increasing the mixing, so we're bringing that warm water from the lower depths to the surface, where it diffuses and so forth. That Arctic Ocean, for a small little body of water, has major impacts, as does the Mediterranean. Because again, as I mentioned, the North Atlantic Intermediate water originates in the Mediterranean, and the Mediterranean is cooking.
Yeah. Yeah. Crazy. Okay, look, I'll move over because this more people want to ask questions. Thanks, Kaisa.
Okay, thank you, Peter. Next, we are going to bring on Jonathan Cole. Jonathan is a physicist and climate innovator from Northern California and has been designing and prototyping reflective solutions for global cooling since 2014. With a second passion for creating compelling visuals, he also develops websites and infographics for climate cooling solutions. So glad that you could be with us today, Jonathan.
Thanks. Jim, your excellent portfolio of YouTube videos are all on topics that are really key to understanding the oceans and finding climate solutions. So I just wanted to thank you for your body of work.
Well, thank you.
Yeah. So getting excess heat away from the biosphere of any planet is very challenging in any kind of short time scale. So when a group of students with 1 or 2 years of physics is asked for ideas to get excess heat away from the biosphere, they'll always come up with one idea, which is to send it to the deeper oceans, where it will take hundreds of years for it to reemerge to the surface. You know, visualizing pumping mechanisms, for instance. But when you ask the same question of a 3rd or 4th year physics student, they generally come up with the counter argument, which is by allowing the surface of the ocean to get very hot during the day and stay there at the surface, it allows it to emit that heat during the night at a higher temperature than it would otherwise be, which, because of the power law, allows more energy to leave during the cold of the night. And actually that heat then leaves the Earth system completely to never come back. Whereas if you put it down deep, it will come back after a certain amount of time. So where do you stand on this issue about whether, you know, if it wasn't possible to develop technologies to change water from the deep to the surface and reverse, about whether it would be better to hide the heat down deep or to bring it to the surface and let it emit?
Well, 1st and 2nd year students are correct that you could sequester the heat to depth, which is what the thermal hailing flow has historically done to help moderate the climate. So they're not incorrect. You know, as I showed in that graphic there, a lot of times the heat got sequestered to depth, along, by the way, with the CO2. You know, so now as to, you know, the nighttime cooling and so on, sure, that happens, but that's just the upper few meters. We have heat that's accumulated and it continues to accumulate in the upper 500, 700 meters. So like with anything else, and this is what I've done a lot of work on, you have to construct heat budgets. What are the sources? What are the sinks? It's tedious work. It's not easy, but you just sit there and you have to make the assessments, make the calculations as best you can, and figure out what the overall net is. This is what the folks who calculate the EEI do. But again, they fail to take into account the diffusion of heat from the ocean. So yes, you do have nighttime cooling to the atmosphere. And if you have cloud cover or not, the heat can either escape to space or not. But that's just the upper few meters. You have to look through the whole water column. And when you look at the accumulation through the whole water column, that tells, again, thermodynamics informs us otherwise. So, and another thing I want to mention, when you measure, I didn't mention in the talk, and I'll probably mention that now. There are several ways to measure sea surface temperature. The most ubiquitous way and most convenient way is to have satellites buzzing overhead. Well, they buzz overhead, they send out their frequency that they're programmed to. But what are they measuring is the skin of the water, right there at the air-water interface. They're measuring the skin. To measure a meter down, 2 meters down, 5 meters down, 10 meters down, you need buoys, you need ROVs, you need to go out there on a vessel and drop CTDs over the side. You need to collect other data. And it's for the same reason that the measurement of SSTs just by satellite alone can be biased and misleading, is when we measure air surface temperature, do we place the thermometer right on the ground? We don't, right? Because you get the immediate absorption, right? And it can bias the temperature upward. So what do? We take the standard procedure, the protocol is to measure air surface temperature we measure 2 meters high. That's where we measure our air surface temperature. Now, I will admit, and we don't have a standard in the oceans to where we measure sea surface temperature. We don't. Is it right there at the skin, between water and right at that interface? Is it a meter down, 2 meters down, 10 meters down, 20 meters down? Do we measure through whatever depth is and then integrate over and take the average value of it? And then, there's your sea surface temperature. I've been pushing that we should have a standardization like we have for the atmosphere, and that would be 2 meters down. You have 2 meters up for the atmosphere, 2 meters down for the ocean. So that's something that needs to be decided on. I'll be honest on that.
All right, thank you.
Thank you so much, Jonathan. So now we would like to open it up for a couple of questions from a few others who have written in. And we have a question that's, just a reminder, everybody can send your questions over to Barbara in the chat. Actually, I think it's showing up as Meer in the chat. Yeah, you can write to Meer if you have a question, and I will ask it. So John is asking on the point about the 93% excess heat being absorbed by the ocean. When was it zero, or has it been significant like that for a long time?
Okay, the 93% is how much energy that burning of fossil fuels that's been introduced into the system has been absorbed by the ocean. So in other words, if we burn X amount of fossil fuels, 93% of that resultant heat from burning that amount of fossil fuels ends up in the ocean. So when was it zero? Before humans started burning stuff. I'm not to be glib on it, but that's basically it. So I wonder if that wasn't clear. Let me make that clear. That when I talk about that 93% absorbed by the ocean, that is the heat energy that humans have introduced to the system being the Earth planetary system, from direct burning of fossil fuels.
Okay, that's very clear. And here's another question also from John. Do you have any idea of extra heat entering the Arctic since 1980, contributing to the start of sea ice retreat? What is the heat power due to Atlantification? John has estimated it's 0.25 to 0.5 petawatt, but would like to see an actual calculation.
I don't have the numbers offhand, but
Mhm.
I do know that yeah, we've done work measuring that in the units indicated. In fact, if you look at the breakdown, I think it was the same units. So when I did the ocean, region by region of the ocean, I think it was also the same units there. But we do measure that. We do the heat budgets and so on. We also know that when we have the inflow of water from, say, the Atlantic side there, that's bringing in heat energy. So we try to get a handle on how much heat energy is being brought in with that inflow. And then we try to calculate it. There have been numerous studies been trying to get a handle on this. I mean, the Arctic Ocean may be a small body of water, but still a big place. So it's difficult to, and unfortunately now with the current geopolitical stuff, we're not getting the information now from the Eurasian side, unfortunately. So we're losing out on that information, which is extremely sad because some of my colleagues were from Russia. So it's very sad. It's very sad for science. It's now depleting. It's diminishing. It's hurting our understanding of the system and the dynamics going on. It's very unfortunate.
Yeah. Okay, here's another question that's come in. How dependent are the oceans on the AMOC for oxygen and nutrient circulation? Because you mentioned about the oxygen and nutrients. The decline of AMOC must be worrying.
It is. For what I tried to outline in my presentation, that as AMOC, it becomes a North Atlantic deep water, and that flows southward. It eventually upwells off Antarctica, the Antarctic divergence zone. Well, it brings in a whole load of nutrients and bring those nutrients into the photic zone. The phytoplankton go to town, do their thing, and then you got little zooplankton eating the phytoplankton, and you got little bigger zooplankton eating the smaller zooplankton, and so on and so forth. You get the krill, you get the baleen whales and the orcas and so on. So a slowdown in AMOC, the slowdown in deep water formation and flow, will have a very bad impact on the food web and productivity in the Southern Ocean.
Mm-hmm. Very disconcerting. Here's a question from Lowell. Al Gore talking recently at the World Economic Forum, stated that if net zero is reached, the warming would stop almost immediately. What is your opinion? I know you mentioned there's this lag point. I forget if you said was 20 years later or 15 years later, we'll see what the warming was in the ocean.
Yeah, as much as I admire Mr. Gore, I'm not in agreement with him on that one. We have the pipeline warming, we have the lag effect, and we have all that ocean heat content just waiting to do something. Right. And it's going to do something. It's not going to be very pleasant.
Well, just one other question, and then I have a question myself. One question, what role do natural aerosols from the oceans play in generating aerosols and forming clouds naturally? And what happens if those natural aerosols are disrupted due to algae diminishing?
Well, that's a very good question. There are many forms of biogenic, sources for aerosols. I mentioned the DMSP and the DMS. Those are the major ones. There, you also have sea salt aerosols, typically along coastal regions for obvious reasons, wave actions and so forth. As the oceans continue to stratify, less and less nutrients get injected into the photic zone. Net primary productivity decreases, meaning the phytoplankton decrease. So that means there will be less and less of these compounds released into the atmosphere, and these compounds serve as like the aerosols from the sulfur, the fuels, shipping fuels. They serve as hygroscopic particles for the water vapor to coalesce around. Well, if they're producing less of those compounds, there's going to be less hygroscopic particles to form the clouds. So think of that as a positive feedback loop, which only exacerbates the situation. So that's the main issue. There's another thing to remember about phytoplankton. Phytoplankton release 55 to 80% of atmospheric oxygen. Phytoplankton start dying out, less oxygen. And by the way, we are measuring a decrease in atmospheric oxygen. I mean, I'm going to be blunt here. Between all that's going on in the oceans, the overfishing, the pollution, and so on, the oceans are dying. I have to be blunt about it. The oceans are dying. And if they're dying, so are we. I mean, I hate to be so morbid about that, but that's the reality.
So that kind of leads into, if we saw the graph for your, personal level of panic. I mean, how do you hold all this, and do you think about it all day, every day, like the moment you wake up? Are there periods of time where you can be distracted from the knowledge of all of this?
Well, maybe because I don't have children, so it's like I'm just, I don't have many years left myself. So yeah, I just, I don't, I also look at it with the understanding that the fate of all species is extinction. So we just happen to be accelerating ours. But what's sad is the species we bring along with us, we drag down with us. I mean, I was a co-author on a paper, peer-reviewed paper published last May. Yeah, something like that. And we were talking about the factors not considered with mass extinction events, something like that title. I was tasked with the role of with the duty to discuss mass extinction events in the oceans and what are the major factors causing that. It turned out to be the big bulk of the paper. Oh well, but I identified four or five major factors and then two more modern factors. One was increasing ocean water temperature, increasing acidity because of the CO2. CO2 plus water makes carbonic acid. Increasing stratification, decreasing oxygen levels, decreasing net primary productivity. When one or two of those factors were in place, there was mass extinction events in the ocean, definitely a mass reduction in genera, in the number of individuals of species, and so on. Well, all five of those are in place today now in the ocean, and add in overfishing and plastic pollution. Mm-hmm. This is why I say the oceans are dying. But as to, not always thinking about it, well, I go and listen to Emerson, Lake and Palmer, Renaissance Genesis, or something like that.
Yeah, well, it's important to take breaks. We are so grateful for you spending this time and sharing all of your vast knowledge about these complex systems. Thank you so much.
And thank you for the invite, and it was a pleasure being here. If I may, for anyone who may not know, as John mentioned earlier, I do have a YouTube channel where I discuss a lot of things. In fact, my presentation, I'm probably going to turn that into a video and post it to my YouTube channel. But I do have a YouTube channel. It's called Science Talk with me, Jim Massa. Excellent. And I have a lot of things there on the ocean. I tend to concentrate in the oceans for obvious reasons. But and I talk about other things as well. But yeah, I go there. I've been going through my videos, trying to create put the videos into appropriate playlists and so on. But I also did a series of videos talking about the various oscillatory systems of the planet. like the North Atlantic Oscillation, ENSO, all that kind of stuff. They're detailed, deep dive videos. So you can check those out. I did one on rotating systems. So if you really want to understand how gyres in atmospheric cells form and all that kind of stuff there, and Ekman transport and Ekman pumping, there's another one.
Okay. And we've written that link into the chat, Science Talk with Jim Massa. Yeah, thank you. We will look for you on YouTube. And thanks again. At MEER, we're working to help educate the public while also developing a solution to warming on the planet. We invite you to keep learning about Earth's energy imbalance and climate science on our website. We're primarily a volunteer staff, so please consider making a monthly donation of any amount if you have enjoyed being here and learned a lot, like I think many of us have today. Also, check us out on either our YouTube channel or social media. If you have found being here beneficial in some way, please tell somebody you know about MEERTALK. And we hope to see you all again for our MEERTALK on April 6th, when Dr. George Tsaloudis will be presenting. Thank you so much for coming, everybody. Bye for now.